Thank you all for coming to my talk today, and thank you for hosting me, Paul. Appreciate you all coming down tonight. As the title, self-explanatory, hafnium oxygen isotopes, Permian intrusions, Cordillera Frontal in Argentina. Just thank you to my supervisors, Stefan, Tony and Marco, for all their guidance over the years, and a few collaborators, Heejin, Ian, Eduardo and Nora, for the Geological Survey of Argentina, and sponsorship also from the Australian Government for the PhD scholarship, CCFS for a lot of the funding to go towards analysis, and SEGMA, the Geological Survey of Argentina, for the fieldwork support and transport of samples, which is quite key coming back from Argentina. So I'll get started. The aim of the whole PhD project was to look at a tract of intrusions that occurred in the Permian, which is, as people might know, in the Andes, is a little bit older than the common exploration target age, which is normally in the Eocene to Miocene for most porphyry and epithermals. This is a preservation thing where they're either older porphyries or epithermals or either undercover or have been eroded away. So the project was to understand the spatial temporal evolution of this set of intrusions, to understand the magma sources, how these are formed, the petrogenesis, how they regionally correspond to intrusions over in Chile as well, and what this actually means for exploration and a tectonic setting to develop back in Permian time. So just to start you off, this is a compilation from Singer 2008 of just global porphyries known around the world. A few big ones, obviously, from the left-hand side in the Middle East, the Tethys, over to Central and Eastern Asia, down into Southeast Asia and the Pacific, Eastern Australia, and over the right, North America and South America, the largest of the belts known today, non-continuous in segments, and we'll go into that a little bit more. But this is a global phenomenon, and most of these settings are in your Cordillera-type subduction settings, where you've got a continental plate and you've got an oceanic plate being subducted. But in saying that, there are a few other settings where porphyries can form. So in the top left there, this is your classical subduction tile setting. You've also got collisional, which is more of your Tibetan, if anyone knows about them, style setting. There's also known systems to occur in delamination and post-subduction extension. And we're hoping to show that there's actually a little bit of a link possibly between subduction style and post-subduction extension before extension prevails too much and you get back arc rifting, really. So just to understand that in a Cordillera or Andean style magmatic arc, Jamie Wilkinson showed that there were 4 precursors or triggers for porphyry formation. You start at number 1, deep down in the mash or the hot zone. You need to develop this area. Then there's a few steps that make sure that your chalcophyte and cytophyte elements enter into the melt phase and actually are able to mobilise into the upper crust. And then number 4 is actually precipitation out in the upper crust, where your porphyry will intrude at 1 to 3 kilometres depth, also into a favourable host rock. So actually transitioning from lower to upper crust, we want to actually find out in this project down into number 1 in the lower crust in the mash or the hot zone, what's going out in magma sources and how porphyries form. And if you get to a volcano, it's not the best for porphyry formation. It means your chamber's a little bit too high and it's going to erupt. And porphyry mineralisation is not well known. In some instances they do occur, but not the best. So where do we go? The Andes, of course. Andes have been subducting for over 330 million years on and off in certain epochs. And so it's good to track long-lived magmatic arc systems. They're also known for large mineral endowment from Peru to Chile. In these kind of areas, these large porphyry magmatic systems, IOCGs, skarns, epithermal. So it's a very well-known area. And they also have very good Malbec and great barbecues. So it's not the best, it's the best place to go and actually study for 4 months, which I'm pretty happy about. So I've literally stolen this slide from Timothy Island, and he's actually in the crowd. I didn't know he was going to be here, so I'm very red-faced that I've stolen this on him, and I haven't even written his name on there. I was going to mention him. He's actually in my notes. But this came from his slide that he presented at the CET back a few years ago. And he showed, and which what we're trying to show is that over the 300 million years, this is a database compiled from Singer 2005, the USGS, and it shows age over contained copper. These obviously are 2005, Escondida, Chucky, El Teniente. Some of these have nearly doubled in the resource size, so these peaks are well and truly off the scale at the moment. But over the 300 million years, and this is a preservation issue or undercover, some people think unfertile or unfavourable. This is one of the deposits we've been studying, Cenozoic, copper, gold, porphyry. It's a blimp on the radar compared to your younger Miocene and Eocene systems. So this just shows you over 300 million years, the contained copper. This is your current exploration age people are looking at, and this is a little bundi down here on the left. So Tim actually showed that if you actually look at HASC 2002, the lanthanum-ytterbium ratio of the rare earth patterns, that there was epochs of compressional events that lead up to a relaxation of the arc, and then that is when you then get a resetting event, and then it becomes compressional again, and these patterns in the younger years actually lead up to where you get your major porphyry formation. If you can also follow that to Lauch's unpublished, we could all go and sift through the data, but he's done it already. Strontium over yttrium ratios, and he actually tracks this as well, these ramp-up events to where most of these major mineralisation events occur. So this is meant to track compression, go into a phase of stagnant or near neutral stress, and that's when you get your porphyries going into the upper continental crust and forming a deposit. So this just shows you that what was happening back in the Permian Triassic. Is this unfavourable? Was there not this compressional setting that we see in the younger arcs? So just go to the Andes, a bit of the basement, as you can see, South America, Amazonian craton, and most of the time during the Paleozoic, the western proto-margin of Gondwana was a series of allochthonous terrains. Some of the ones in the south, which is shown over here on the right, Famatina, Cuania, and later Chileni that comes onto the back as well. These are allochthonous terrains that came from the Grenville orogeny and accreted to the proto-margin. And this becomes quite interesting of what is your basement host rock of a lot of these systems that are now coming up through this mash or hot zone and developing over time. So this is quite well studied. If you then go on to our target area, the Gondwanian orogeny, this was a time between the Carboniferous into the Permian and then the Triassic, and this actually was a period that went from compression to slow transition then into extension. But that's only been known from whole rock geochemistry from a volcanic province called the Choyo that erupted in the late Permian to Triassic from around 280 to 250 MA. But the intrusions, because it was a large volcanic province, and that's highlighted in the red over here on the right. So it goes down as far as Patagonia, nearly about the same size as Spain. So this is a rhyolitic to andesitic volcanic province. So it actually covered up a lot of the intrusions that occurred during this time. But if you notice this little blue box here and the stars, this is the Cordillera Frontal, where we have this set of intrusions that are exposed and have been unearthed. And this is where we'll be looking and taking most of our samples from. So it's a very interesting area too, that this is actually the opposite to what you see in modern day arcs, from compression to lead up to extension. This is going from compression to a period of extension into the back arc, but we've actually got, instead of a short time frame, we've got nearly 30 million years of relaxation. So maybe this isn't the most favourable location at the time if it's extending for too long, but we'll find out a little bit more about that. Next. So if you know about the Andes, Silito and a few others over the years have actually tracked, and many others have known that mineralisation in the Andes is restricted to certain tracks that are spatially and temporally related with mineralisation. And if you head out of these belts or tracks, you start to step into unfavourable territories. And some of these tracks that you might know about, El Teniente was, and a few others, are associated with the subduction of oceanic features like the Juan Fernandez or the Nazca Ridge. And so these areas are actually well explored for at certain times and certain areas for magmatic mineralisation. So your porphyry, epithermal, skarn, and in certain areas ICG in northern Chile. We'll just zoom into some of the older systems. There are some there. If you just look on the right here, this shows some of the Cretaceous on the left, and on the right, the smaller known belts in Argentina is the one we're studying, and then to the northern Chile is another belt that's actually quite near synchronous with the main magmatic arc that go. And this extends down to the south in La Voluntad, and there's this track, discontinuous, maybe undercover or destroyed later on. But this is our area around Mendoza in Argentina, San Jose, Jaguaras, El Caparoso. We have samples from these porphyry systems, and we'll show you a bit of the data. So fieldwork, as Paul said, 4 months in Argentina. It's terrible hard work. As you can see, you get chased by pumas during the fieldwork. You get to hike nice big mountains. You go to large, old, this is Castaño Viejo, polymetallic, zinc, lead, copper, silver, gold system that was mined heavily through the 60s and 70s, is now well abandoned and flooded. And then this is a core sample from San Jose. This is massive chalcopyrite, pyrrhotite and pyrite, and a nice grain of sphalerite. So this is a deposit that is actually trying to get across the line at the moment with environmental concerns. And another just shout out to supervisors, Stefan doing a nice jump shot at El Caparoso, and Stefan, myself and Marco, we had to get some horses to get up and sample one of our areas, which was a lovely long sore day in the saddle, but a bit of fun. So why zircon? Main reason for us is it's a resistive mineral. When you're in a hydrothermal system like a porphyry or an epithermal, alteration becomes a big problem. And so when you actually get in this overprinting event, you can't trust the whole rock geochemistry as much. So we look then for the resistive minerals like zircon, which we can try and extract information out of, such as geochronology. We can get good absolute uranium-lead ages on. We can understand about its petrogenesis through certain isotopic schematics. They're abundant in arc magmas, so they're quite easy to extract. And they're also routinely analysed and studied over the past few decades. So this is not a new mineral that we're exploring into. It's well studied, so we can document it quite nicely. So this is just some of the mounts that you've got to make and some of the CL images before you zap them on some of the machines. So just a little bit into the zircon isotope systematics. Uranium lead, geochronology, gives you a nice good age. Oxygen isotopes, this shows you how much sediment's been incorporated into the magma, possibly in that mash or hot zone, or as it's arisen into the upper crust, but not as likely. It also shows you if you're getting then crustal recycling at that time as well. Lutetium hafnium, this shows you if you've got pristine, juvenile, mantle-derived magmas coming up, or if these are crustal magmas that have been incorporated again. So this can give you a little bit more information about the deep systematics down in the lower continental crust and what's happening in this mash or hot zone. So a few of the machines that we get to play around on, combination probably worth a few million, so don't want to stuff them up. But the shrimp up here at ANU and Curtin, invaluable for the uranium lead. You give a nice, precise age. The Kamika 1280 at the CMCA at UWA down the road to do our oxygen isotopes. And then the Neptune at the School of Earth Science, UWA, to do our lutetium hafnium work with Supervisor Tony. So it was quite nice. So here's just a regional map of our area. Here is Santiago, here is Mendoza, San Juan, and these are just some of the areas, or the ranges they like to call it, which is Cordillera is Spanish for range. So you've got the coastal Cordillera, you've got the main arc where it sits today in the principal Cordillera most of the way, then the Frontal Cordillera in the purple where we're studying, and then you've got the pre-Cordillera as well. And so if we just zoom into our area in the Cordillera Frontal, this is the pink not the best colours to use, I apologise. The pink is the intrusives from the Carboniferous to Permian Triassic, and the green, which doesn't pop out any better, this is the Choyo volcanism. And as you can see, it's quite large swaths, and only in certain spaces do you get these intrusions pop out. And the mineralising systems actually sit on the eastern edge of actually the outcrop, where it actually hits this basin here. So these systems are actually being, they're eroding out of the hills. You've got the Choyo volcanic group overlying, and then these are actually coming out of the hills as you're exposing them. And these are all new zircon, uranium, lead ages. So some of the older ones occur down at Jalgadas and Cenozoic around 282, 280. And further north you get a few other ones, 270, 260. And our youngest ones are late Dicras at 252. We did sample a few more, but sadly they came out to be Miocene, so we actually threw them out. Maybe another publication down the track. So if I then take, I'll go back one actually. No, I'm not going to go back one. If we look at a regional data set of uranium lead ages compiled from Chile and Argentina, I'm just going to show you how spatially and temporally the arc evolves over around 100 million years. Again, I apologise for the colours. It comes out here nicely, but not so much here. There's a track here of intrusions that occur from 330 MA to 285. These all occur in Chile. These are our oldest ones from the Carboniferous to early Permian. If we then go in the mid-Permian from around 285 to 265, we see then a shift eastward around possibly 120 up to nearly 180 kilometres inland of the arc. This is where we see our mineralising events, and these extend quite a fair way south down to around -38, -39. If we then go one more step into the late Permian, 265 to 250, not very well known for the mineralising systems. It does a couple, one or two areas, but this now extends across the spatially same place, but extends a bit further back over and joins the main arc, which we see earlier. And then if we then go into the Triassic, 250 to 220 MA, we see the very isolated areas, pockets of intrusions up in the north in Chile and then to the south. This is obviously reliant on good sampling, and obviously, as you can see, possibly these studies didn't extend over into Argentina. So further sampling will define if this shift is real, but you can see that especially down in the southern areas, there is a large shift towards the east, inland, like I said, up to 200 kilometres nearly, of the arc magmatism. And this it continues for another 50 million years nearly, before we then see a resetting, and then actually along the far eastern edge of the Cordillera, you actually get these back arc basin and rift basins then filling in with sediments during the Triassic, which is our large known extensional regime. So just to show that spatially, you can see that this large shift eastward, and to represent that, and well, our mineralisation. And this is to say these are really the only mineralised systems known to occur in a certain area. And I'll show a few later on that we might be able to predict a little bit more. So possibly there's two explanations to this. You've either got the arc migrating and it's gone in 150 kilometres, 200 kilometres, or you're getting the development of a rear or back arc extensional environment. And we believe possibly that the extensional environment is a little bit more likely than the arc shifting 150 kilometres eastwards when we're heading into an extensional regime. So just back to our data that we've got, age, so I should go on the y-axis, we've got latitude, north-south. On the top one in A, we've got our age, and this is showing that some of our southern localities are our oldest, and heading north there is a slight, maybe younging trend, not the best, but it will be good to know that early, intermediary and late magmatism, and I'll show you on the couple of slides later, these aren't quantitative known belts, it's not very well defined, but just remember these different pulses and we can show that possibly how the isotopes develop. And just in the bottom here, we've got again latitude on the left, delta 18O, our oxygen isotope, and on the right, epsilon hafnium at the time of formation on the right, and possibly there is a lightening of some of the samples as you go from south to north, and the same in the hafnium as you're getting a bit more crustal values in the south, and as you head north, some more mantle-like values, except for the one from our Permian that doesn't really fit. So if we then show this, same again, delta 18O and epsilon hafnium over time. So if we go from start at our oldest magmas at around 282 MA down to 250, in the top one for the oxygen isotopes, we see this lightening continue down and a few in this early magmatism around those mantle values. And in the epsilon hafnium, we see this convergence coming from the two different, it's like an arrowhead pointing towards Chur-like values. So we're seeing these values evolve over possibly 30 million years as the arc continues. So if you go then compare your isotope ratios, and this is where I said remember your early, intermediary and late magmatism in the red, green and blue. And this is epsilon hafnium on your x-axis, and your y-axis you're at your delta 18O as your oxygen isotopes. And as you can see that your oldest samples have a crustal-like value at around 8. Mantle-like values as derived by John Valley back in 1998 sits at around 5.3 plus or minus 0.8, and with positive hafnium ratios shows more of a mantle-like signature. So you're actually showing that your two end members are a crustal source or a supercrustal source, and a moderately depleted mantle-like crustal source, and mantle source, sorry. And then as you have the interaction over time, over 30 million years, you're getting a hybridized signature between the two end members. And it actually then shows that none of these are spatially associated, so none of these are directly only porphyries or epithermals. These are all mixed signals. So other authors in the past have noticed that you might need certain mantle sources to be associated with gold, copper-gold mineralisation in porphyries, and more tin-tungsten systems with a lot of sedimentary input. We don't see that. Our actual copper-gold systems actually plot up where you'd see your tin-tungsten. So there's no exclusive one isotopic signature for a magma that can form a deposit. But this hybridization between the two end members is quite interesting, and it's a very unique data set that hasn't been as well shown here in other studies. So if we actually understand then how these magmas form, this is from, sadly, the late Jeremy Richards, and this is just showing your magmatic arc, your fluids deriving off, creating your basaltic magmas that go up into your lower crust, into your mass or hot zone, and then slowly feed up into your upper continental crust to form your system. And if you actually take out this upper part, this is a model proposed numerically by Catherine Annan back in 2002, and then subsequent work done in 2006. And this is what they label the deep crustal hot zone. And the model shows that in this area where you're getting the periodic injection of hydrous, hot basaltic magmas into what you'd say at the time, a cool, lower continental crust. As you get this periodic injection, you get your basaltic melts exchanging temperature and volatile fluids with the host rock, whether it be a peelite of some sort of metasedimentary rock. And it will not only have a percentage of melt from the supercrustal source there, but you'll also get these cooling residual magmas from the periodic injection and the cooling of the basaltic magmas. So this model explains exactly what we just showed, that you're going to get these, and this is direct isotopic evidence to support Annan's work, and it's not new, but it's quite unique, that you're going to get these mantle end members synchronous happening with your crustal end members. And then over time, as you get the continued periodic injection of basaltic material, you're going to maybe increase the signature of a mantle, and why you might get a pulling away from your supercrustal, and you'll see the hybridization of the melt. And that's the model that we've proposed that actually fits quite nicely with what we're looking at. So if we then go and take a regional compilation, and sadly this is not the most well-studied area, but there are 37 intrusions that has comprehensive uranium, lead, hafnium and oxygen done on zircon. I'm not going to start to go on anything else, just on zircon at the moment. And these actually expand a period of around 100 million years. So it's quite nice then to show how these isotopes evolve over 100 million years. So just some of the authors, Jones, Del Rey, Heve and Descartes, of this work, and the colours will correspond with the next diagrams that I show. So if we just then look at the oxygen isotopes, so crustal values up around your 7, 8, 9 per mil, and your mantle-like values as determined by John Valley, around your 5.3 plus or minus 0.6 at 2 standard deviations. So as you notice in the green ones, which are in the coastal Cordillera, have this crustal signature at around 310 to 320. As you continue along and you get a bit more magmatism up in Chile, you get a little bit more, lower continental contribution towards mantle. Then when you actually get this shift or arc migration over east, is when our systems occur and we get this mantle signature synchronous with this crustal signature. And as it continues over that 30 million years, you move the arc back over into Chile and continue on down into a mantle-like value. So this shows over 100 million years, you're going from a crustal signature transitioning into a mantle-like signature. And this is also, very nicely, coincidentally, reflected in your hafnium isotopes, where you've got negative hafnium values showing a crustal-like source, and then over 100 million years, you've got more of a positive hafnium signature, which shows your mantle-like values down here. So this actually corresponds quite nicely, and especially at your time frame of when you get the arc migration over into Chile. Now, why is this important, and why would we care at all? This time period in this shift with your arc migration, back arc extension, is our mineralisation window. And over this 100 million years, this 20 to 30 million year period is the only period known for mineralisation across this 100 million years. So this event that led to the back arc extension or arc migration, this is the event that actually caused mineralisation to occur in the Cordillera Frontal. So this is nicely recorded in our isotopes for over that 100 million years. So if you put that into a tectonic implication, if you look over the left here, there's 3 stress regimes an arc can be in at any one time. From the top, this is a compressional regime or a coupled margin, where you've got the overriding and underriding plate compressing together. You don't get much of a magmatic arc. This is actually quite compressive. Then you get B, neutral or a stagnant near neutral stress regime, where you're actually getting a kind of a stagnant setting in the overriding plate. And then in C, we get a decoupled margin or an extensional margin, where you're going to see back arc basins forming. You'll see slab rollback or arc retreat. And what's quite nice is that we believe in this near neutral or transitional zone from compressive shortening to back arc extensional regime. This transitional period where it goes into a stagnant or state of near neutral stress is where we see our porphyry formation. And that actually shows here on the right as well that if you're going to have a compressive margin, you'll actually get more of a crustal incorporation. You'll allow magmas more time to incorporate supercrustal material, where if you then go into an extensional regime, you're going to allow the influx of more basaltic material into the hot zone, and you'll allow for that dominant mantle signature to occur, which we track over nearly 100 million years. So then what does this have for exploration potential if you are looking in the Permian Triassic, which not many people are, sadly. But here is our mineralising systems that we see in the Cordillera Frontal. There are 3 other known systems down south: Josephina, a tungsten system; Infertile, a copper moly in the San Rafael Massif, and La Volontada, which is a little bit older, but the geochron's not very good on it, a copper moly system down south, which could be incorporated. Patagonia sits a little bit further down south. So we're hoping to show that the regional actual magmatism that tracked this extensional period, not only from up here in the Cordillera Frontal, but extended down south of these intrusions that we see from these black dots, that there's actually the potential for further exploration in this back arc setting that is extended down further south. And this hasn't been documented because this is the main focus of the Permian Triassic area in the Cordillera Frontal. But once you go down south and you track this magmatism, there's a whole nother area which is potentially to hosting porphyry, epithermal, skarn-like mineralisation in this back arc extensional regime. So, in summary, and not to bore you and take you away from the rest of the bar tablets sitting upstairs, we've been able to show that through good absolute geochronology that we've redefined when these intrusions occur from 285 to 260, and this is our mineralisation window, that we have a variation slight in the isotopes, a long strike from south to north, and that if you compare the oxygen and hafnium isotopes, you get this contemporaneous mantle and crustal-derived magmatism, which will correlate with a deep crustal hot zone. We've shown that we've shown with the regional compilation of data through the arc migration, which is more going to be associated with your back arc or rear arc extensional, and that over the 100 million years you're going to develop from a crustal signature to a mantle signature as supported by the deep crustal hot zone. And that our mineralisation window is going to occur when the magmatic arcs in a state of near neutral or stagnant stress that's going to allow these systems to arise into the upper crust, and that potentially there is a new area continue the Permian Triassic belt from the Cordillera Frontal down further south into this extensional area. So thank you.